Alright, welcome back. In this video, we are looking at lesson 4 of unit 1, and this is limits to infinity and also infinite limits. So this is two different things, but they are very, very similar, but they're just for whatever reason in very different places in our book. But that's okay. So, for section 2.4, we're looking at infinite limits. Can you look at these graphs and figure out what the limits are of each of these functions as we're approaching 1 from the left and from the right? So for this one, as we're approaching 1 from the left, we're going down to negative infinity. As we're approaching 1 from the right, we're getting positive infinity. So our limit as x approaches 1 of this function does not exist. What about this one? Well, we're getting positive infinity from the left and positive infinity from the right, but is this limit going to exist? The limit as x approaches 1 of f of x for this function 1 over x minus 1 quantity squared, this again does not exist. If you want to be specific and you want to say, well, yes, I do know that this is both sides going to positive infinity, then you can put that, that's fine, but you also need to recognize that the limit does not exist because infinity is not a number. For this one, we got the limit as x approaches 1 of f of x. What's going to happen here? Well, we are going to positive infinity when we're approaching from the left, and we're going to negative infinity as we're approaching from the right, and so those are different, and they're also not numbers. Our limit, you guessed it, does not exist. And finally, we have our limit as x approaches infinity of f of x here. So coming from our left, we're going to negative infinity. Coming from the right, we're going to negative infinity. So we can say, this is as x approaches 1, not infinity. As x approaches 1, this is going to be negative infinity, that's true, but it's also important to recognize that the limit does not exist. And these are all where we have vertical asymptotes. So we have a limit way of describing what a vertical asymptote is. So it is when you have a function approaching infinity or negative infinity as x approaches c, and the c value is an x value, from the right or the left, then the line x equals c is a vertical line, right? Because we get all of our x values are on the x-axis, so if we get a vertical asymptote at x equals c, this is at c, that's a vertical asymptote for our graph of f. So, if we have our limit approaching positive or negative infinity for our function when we're going to a particular finite c value, which is an x value, it's something we're putting into our function, then we have a vertical asymptote. So, going with this, can you think about what possibly our horizontal asymptote definition could be? That is something for slightly later in this video. So, let's look at this. We have f and g continuous on our open interval containing c. So that means that we have continuity. Continuity means that all of the other things in math don't break yet. We have, we have scalar multiplication, we have addition, subtraction, multiplication, and division as long as our denominator function is non-zero. Okay, so that's nice. Now we're saying, if we have this condition of f of c is not 0 and g of c is 0, so now we have our denominator possibly is going to be 0. There exists an open interval containing c such that g is not equal to 0 for all x is not equal to c on the interval. So there's going to be somewhere where our function is not, our g function is non-zero for that interval. Then we have a vertical asymptote when our denominator function is going to be 0, but you have continuity everywhere else. And that's going to be our vertical asymptote at x equals c. And that is very, very close to what our definition of vertical asymptote is, because when we're looking at the limit of this, we're going to get out an infinite value. So our limit is not going to exist due to the limit going to positive or negative infinity on the right or the left, or both. So, let's look at this. Determine all the vertical asymptotes for the graph of function A, for the function in A, the function in B, and the function in C. So, pause the video, think about where our vertical asymptotes are going to be. Hint, hint, it might or might not be when our denominator is equal to 0, given what we were talking about up here. In our first function, where we're looking at 1 over 2 times x plus 1, we know, just looking right here, that we can say their denominator is going to be 0 when x equals negative 1. So that means that we're going to have a vertical asymptote at x equals negative 1. If we're looking at the graph of the other, well, this is a difference of squares in our denominator. The numerator is a sum of squares, which is not factorable. So if we have the difference of squares, that means that we have our denominator is equal to x plus 1 times x minus 1. That means that we have vertical asymptotes at negative 1 and positive 1. And finally, for cotangent, that's denominator is going to be sine, right? Because cotangent is the reciprocal of tangent. Tangent is sine over cosine, so cotangent is cosine over sine. When is sine going to have zeros? Sine is going to have zeros at x equals 0, and also 2 pi, and all the 2 pi's plus or minus those. So that is where our vertical asymptotes will be happening. So in summary, we have f of x is going to be, for a, we're going to have vertical asymptotes, only one of them, and that's at x equals negative 1. For part b, we're going to have a vertical asymptote at x equals minus 1, because our denominator is going to factor to x plus 1 and x minus 1. Our numerator is always going to be continuous. And for the last one, we have cotangent, which is cosine of x over sine of x. Sine of x equals 0 when x is 2k pi, so even pi's, where k is an integer. And so that's where our vertical asymptotes will be. Let's try this one. Determine all the vertical asymptotes of this graph. Well, maybe we can think about what is going to happen for our function if we factor it a little bit. So f of x, let's see, is our numerator factorable? Well, we have for x squared plus 2x minus 8. We need our factors of 1, our coefficient here are just 1 and 1. Coefficients here are 2 and 4, and then we can have a positive or a negative on those. Also 1 and 8, 8 and 1, negatives on those and stuff. So which will give us a sum of positive 2. Well, we have 1 times positive 4 and 1 times negative 2. So if we have x and positive 4, x and negative 2, that should get us where we need to go. Our denominator is a difference of squares, so we have x minus 2 times x plus 2, and that's lovely because those cancel out. So that means that we have a removable discontinuity. Removable discontinuity at x equals 2, and we have a vertical asymptote that's a p, asymptote, at x equals negative 2, because that is when our denominator gets a 0. So let's look at these. So find each limit. The limit as x approaches 1 from the left of x squared minus 3x over x minus 1, and the limit as x approaches positive 1 from the right of x squared minus 3x all over x minus 1. So can we cancel things out with factoring? Let's see. So we have x times x minus 3 all over x minus 1. And that doesn't really get us anywhere, but it was helpful just to check. And when we approach 1 from the left, that means that our value here in our denominator is going to be negative. Right? Because if we're approaching 1 from the left, that means that we have like 0.9999999 minus 1. That's going to be a very small negative number. And then we have a something close to 1. Times negative 2, right? Effectively negative 2 here. So we have positive times negative, which is negative. Positive times negative divided by a very small negative. And so our signs, what happens here, well, we have positive times negative, which is negative, divided by a negative, which is positive. So this is going up to positive infinity. And similarly, if we have the limit as x approaches 1 from the right of x times x minus 3 all over x minus 1, we have a number slightly bigger than 1, so 1.000001 here. So that is a bigger number minus 1, so that gives us a positive in our denominator. So it's like a positive number. We have a positive number here and negative here. That doesn't change. So we have positive times negative. Positive times negative is negative, divided by positive is still negative. So this is going to be negative infinity. So you can think about approaching just by plugging in something close, but just think about the signs. It really helps to factor things, because then you can just handle things as some sign times some other sign, and that's really helpful. And when we're dividing by very small numbers, that means that we're getting up to infinity, or if we're dividing by very small negative numbers, we are getting to negative infinity. So let's look at this. We've got some properties of things. Well, if you have infinity plus another number, then you're going to get infinity. If you have infinity minus a number, you're still going to get infinity. So these still work the same way we think they will. If you have some infinity times a number, you're going to get out infinity. If you have infinity times, or negative infinity, or a negative number times infinity, you're going to get out a negative number. That makes sense, right? So if this number is positive, then you're going to get positive times positive, which is positive. If this number is negative, then you get negative times positive, which is negative. And if you're looking at a division, a quotient, then you have a number divided by infinity, and that's going to give you out 0. And that's also going to work when you have negative infinity. So when this is going to be negative infinity, your limit as some finite thing divided by negative infinity is still going to be 0. Alright, so let's think about limits at infinity. So we thought about what happens when the function is going to infinity. Now, like when the function value is going to infinity, meaning that our outputs or our y values are going to infinity, or our range is going to infinity. But what happens when we are looking at the end behavior when our inputs are going to infinity? So thinking about this, what is happening here in this function? We have 3 times x squared, which is like a parabola. It's maybe like a faster going parabola, but that's our numerator. And then our denominator function is a parabola as well. It's maybe a slightly wider parabola, but that's going to be our x squared plus 1. It's shifted up a little bit, but that is totally fine. What happens as we take the ratio of these two? So, you know, we have 2 locations where they're going to be the same, okay? But then as we go towards positive infinity, this blue, or I guess this ocean colored, divided by this lava color, is going to be a very, very convenient number. So if we're looking at, I don't know, let's plug in a giant number. So what's a giant number? Like 100. It's like the biggest number I can think of. So we have 100 squared times 3. What's that going to be? It's going to be 3 times, what is that, 10 squared, that's 10 to the 4th. And then we're dividing this by 100 squared plus 1. What is that? That's like 10 to the 4th plus 1. So what is actually going to happen here? Does this plus 1 make a huge difference in terms of the magnitude of this denominator? Not so much. So we're effectively getting, like, what is this? 100,000? Is that right? It might be 10,000. I could be wrong. But you have 3 times 10 to the 4th divided by 10 to the 4th plus 1. This is effectively going to get you out to 3, right? This is approximately equal to 3. And if you plug in an even bigger number, then the cause of this plus 1 is going to be even more negligible. So the end behavior that's happening here is that we're actually just going to get closer and closer to 3. The limit, as x approaches infinity, of f of x here is just going to be 3, which is pretty cool. So let's look at this picture. We got the limit at infinity, where we have L is a real number. when we have the limit as x approaches infinity of f of x equals L, that means that for each epsilon, remember epsilon is a y distance, there exists an m, so an upper bound, that such that when we are looking at the distance between our function output and this L that we're saying is within epsilon of each other. So this is within epsilon. We have an epsilon band around this L number. This will work whenever we are looking at a big enough number. And similarly with as the limit as x approaches negative infinity, we're getting an epsilon band of the distance between our function and our finite number L when we're looking at a small enough, when x is less than n. When we're looking at some distance far enough away, after that point, we get all of our function outputs are within epsilon of this L number. And here's a nice little picture of that. So as our function kind of keeps going, even though it's oscillating, right, that's what this kind of looks like, we're looking within this epsilon band of L after an m x value. After some m value. After that, all of the x values that we put in, we're going to get within an epsilon band of the L. So, as promised, horizontal asymptotes are when we have a line y equals L, and that is going to be our infinite limit as our limit as x approaches negative infinity, or our limit as x approaches positive infinity of f of x gives us this number. That means that we have a horizontal asymptote. That means that we are getting closer and closer to number L, which is pretty cool. So, like, if you're looking at, I don't know, if you have 1 over x, right? Your limit as x approaches infinity of 1 over x is going to be 0, and your limit as x approaches negative infinity of 1 over x is also going to be 0. So we have horizontal asymptote, or a ha, at y equals 0, because this is a y value. Okay. Let's think about some numbers. So we have r is a positive rational number. So we got a positive number, and it's rational. That's nice. That means that, you know, we can deal with square roots and stuff. And c is any real number. Then if we have x raised to some power, and we're looking at that in the denominator, and we have just some number divided by x raised to some power, then our limit as x approaches infinity of this is going to be 0. Because if you plug in stuff that's bigger than, like, if you plug in an infinite, like if you plug in infinity down here, then you're getting some number divided by infinity. Even if you're like square rooting it or whatever, you're still going to get out 0. And similarly with negative infinity, as long as, you know, we are allowed to take square roots of the negatives, as long as that's within our domain. And oh, that's what this is saying. This second limit is only valid if our x to the r is defined. That's when x is going to be less than 0, where we're looking at e, our end behavior of e, because e looks like this. E to the x, because e is just a number. It's 2.718 or something. But if we're looking this way, we are getting closer and closer to 0. And similarly, e to the, so this is e to the x, and then we have e to the negative x, which is just reflecting that guy that we just did. E to the negative x. So as we're going towards infinity here, we're getting out 0. Alright, let's try this. The limit as x approaches infinity of 5 minus this 2 over x squared. So remember that we can break this up and think about it in terms of parts. So what are we actually getting out? Well, if we take our 2 divided by x squared, and we're thinking, what is going to happen to that as x approaches infinity? Because like the 5 isn't going to move, right? It's just 5. But we're doing minus this thing. And this value is getting closer and closer to 0, right? Just like what we were saying up here. So if we have 5 minus 0, then what are we getting? We're getting out that limit. The number that we have there is 5. Okay. We're just breaking it apart. Now, look at this limit. The limit as x approaches infinity of 3 over e to the x. Remember that e to the x looks like this, so we're getting 3 divided by like infinity, and what's going to happen there? We're going to get out 0. Oh, we can also rewrite this as e to the negative x, right? Because the denominator we can rewrite with a negative exponent. But for this, we're going to get out 3 times the limit as x approaches infinity of e to the negative x. We know that. That's 0. So what do we get? 3 times 0. Sorry, that's glitchy. Which is equal to 0. Alright. And there's a little bit more. So the evaluating a limit at infinity for this looks vaguely familiar, right? Because we were seeing sort of an example like this in the very beginning. But what is happening here? As we are plugging in bigger and bigger numbers, what's going to actually happen? We're going to get 2 times that really big number, minus 1, divided by that really big number, plus 1. So what is actually happening? Well, we're going to get closer and closer to the ratio of the leading coefficients, which is 2 over 1. Or you can think about this as the limit as x approaches infinity. So we have the ratio of our leading coefficients of 2 over 1. And that works because we are looking at a linear function over a linear function. So the degree of the polynomials, is the same, where we have x to the first power, right, plus or something, some c value. So we have x to the first power in our numerator, and we also have x to the first power in our denominator. We're not using like parabolas or cubics or anything bigger or that will grow faster. So when we're looking at what our limit is, we just look at the ratio of the leading coefficients. The degree of the polynomial, the coefficient, sorry, this is poorly written, the leading coefficient over the leading coefficient. And remember that a coefficient is the number that's in front. Leading coefficient means that we're looking at the highest power, which here is just 1 in our numerator and our denominator. So in example 3, this looks a little bit different because we're considering where we don't have the same degree in our polynomials, in our numerator and our denominator. So here, our numerator degree is 1. Is 1, right? Because we have 2 times x plus 5, and our denominator degree is 2, right? Because we have 3 times x squared plus 1. So, which one is going to grow faster, and which is going to grow slower? Well, the denominator is definitely growing faster, because we're thinking, like, we're taking a giant number and we're squaring it, and then we're multiplying it by 3, and then we're adding 1. Whereas in the numerator, we're just doubling it, and then we're adding 5. So, the denominator is going to get big much faster than our numerator is going to. So, this limit is going to be 0. The options are either 0, infinity, or a number. So, the limit as x approaches infinity of this function, what are we getting? Well, this has a leading coefficient. Our degree of our polynomials is the same, right? Degree 2, degree 2. Let me change colors. And this is non-conventional notation, numerator degree, and denominator degree of 2. So since those are the same, we can look at the ratio of our leading coefficients, which is just 2 over 3. 2 over 3, 2/3. And finally, let's look at this. We have our numerator is a cubic, so that's interesting. And our denominator is a quadratic. Therefore, we have, what? Well, we're going to get a giant number cubed, then doubled, and then add 5 in our numerator. In our denominator, we're going to have a giant number squared, and then tripled, and then we're going to add 1. So, what's really happening here is that we're going to grow a lot faster in our numerator than in our denominator. So, this is going to end up being positive infinity, right? Because we have a giant number, much more giant number in the numerator than in our denominator. So, this limit does not exist. Finally, there's just a little bit more. The Witch of Agnesi is a function. It was made, I guess, or made famous by Maria Agnesi. Definitely someone worth looking into, but the Witch of Agnesi is a function. I think it's just like a mistranslation, but it's a function that looks like this, and it's actually pretty cool. We'll look at it later, but it's like 1 over x squared plus 1 or something. So you have horizontal asymptotes of 0, and you don't have any vertical asymptotes, but you know, it's a cool function. So let's look at the logistic function, which we are going to look at later as well. But the logistic function is, in some ways, it is this. When we have more things to deal with, all of this, then it will look a little bit different. But if we're looking at 1 over 1 plus e to the negative x, as we are going towards negative infinity, so limit as x approaches negative infinity of 1 over 1 plus e to the negative x, what is happening here? Well, we're plugging in negative infinity into our exponent for e to the negative x, so that's actually going to be e to the positive infinity, which is really big. And then we have 1 divided by 1 plus a really big number, so that's actually going to get us out to 0, right? So similarly, as we're looking at x goes to positive infinity of 1 over 1 plus e to the negative x, we're putting in infinity for x. That means that we're looking at e to the negative infinity, and that, according to our end behavior of how what we know about e to the x, right? If we're going e to the negative infinity, that's getting closer and closer to 0. So then we end up with 1 over 1 plus 0. And is this not 1? I guess it's 1 over 1, which is 1. So we have different horizontal asymptotes. As we're going to the left, we have a horizontal asymptote of 1. As we're going to the right, we have our horizontal asymptote of positive 1. It's actually pretty cool. Logistic functions are very cool. There's a lot of applications of them. If you're interested in looking into applications for one of your journals, then highly recommend you just Google logistic function and then anything you're interested in that grows. Be it, world record breaking for track and field rates, or COVID-19 data, or, populations of things, thinking about the carrying capacity of stuff, that is something definitely modelable by logistic functions. So, finally, let's just wrap this up with a couple of examples. So what happens here? Well, we have a degree of our leading coefficient, our degree of our polynomial in the numerator is greater than the degree of our polynomial in the denominator. So we get infinity, or this limit does not exist for A. And for B, similarly, we have our degree of our polynomial in our numerator is still greater than the degree of our polynomial in our denominator. So we're ending up with, negative infinity, but that's still not existing. So negative infinity does not exist. Right. So what did we do? We looked at different functions and what happens as we're considering what their horizontal and their vertical asymptotes look like. The vertical and horizontal asymptotes are can be formalized in the definition of them can be formalized using limit notation, which is pretty cool. All right, bye.